So let me start by welcoming everyone. This is the first talk in the Spring 2024 CDY session, and we are very excited to restart. We had a pause in the fall of last year, but we will be restarting these seminar series. And as you know, we will meet every 2 weeks on Wednesdays, and you can go to the CDY Initiative website, which I will post on the chat, and you'll see the full listing of speakers for this semester. So this semester, we will focus on the topic of particle acceleration and extreme accelerators. And before we start with Gwenael's talk, I just want to mention that the CDY initiative we've been running these now bi-weekly for some time, for more than 2 years now. And we also have other events, which include focused workshops, summer schools. We just had a very successful workshop at the Flatiron Institute in November of 2023 on black hole flares, connecting theory to observations. And one thing we would like to ask the community here, to the regular participants, is we would like to solicit ideas from this group for future topics, workshops that you would like to see. So please send us your thoughts. If there are some areas of focus, any suggestions that you have, it would be great to get your ideas. But today, it's our pleasure to introduce Dr. Gwenael Giacinti, who will be talking. The title of his talk is Particle Acceleration at Relativistic Shocks, AGN Jet and Pulsar Wind Termination Shocks. It's a little different from what we have posted on the website. Gwenael is currently a T.D. Lee Fellow at the Sungda Lee Institute and a tenure-track associate professor at Shanghai Jiao University, and he's a former member of the Astrophysical Plasma Theory Group at MPIK Heidelberg. He received his PhD from APC in Paris, and he has held visiting positions at DAISY, and he was a postdoc at Oxford University. He's interested in a number of topics in theoretical high-energy astrophysics and particle astrophysics, including cosmic ray propagation, particle acceleration, and many areas of gamma ray astronomy. And he's currently working as Science Working Group Coordinator at the Southern Wide Field Gamma Ray Observatory, and also as a member of LASSO and HOG collaborations. So it's a great pleasure, Giacinti, for giving us this inaugural talk at starting us off this semester. So thank you very much for accepting, and please go ahead with your talk.
Thank you very much, Rashmi, for the introduction. So today, my talk will be mostly about particle acceleration at relativistic shocks, in the sense that, in principle, these shocks may be very good particle accelerators, but it's not clear theoretically how this works. And but there is a number of new observations going in this direction and forcing us to think and rethink about the theory of particle acceleration at relativistic shocks. So I'm going to say a few words, to talk mostly about particle acceleration at AGN jet termination shocks, and then I will finish more quickly on a part discussing particle acceleration at the termination shocks of pulsar winds. All right, so most of these works have been done in collaboration with Benoît Serruti in Gwenael in France. All right, so, well, you all know this. You all know that we have very high energy particle accelerators in our galaxy, at least up to several PeV in energy, and outside our galaxy, maybe up to about 10 to the 20 electron volts. So mostly protons, electrons, positrons, and other particles. So here you see the cosmic ray spectrum on the right-hand side, which almost looks like a featureless power law from GeV energies up to slightly beyond 10 to the 20 electron volts. So for sources below the knee, one of the most likely accelerator would be supernova remnants, although now star clusters look like a quite plausible alternative candidate. So we now see the sky in gamma ray from all the secondaries produced by these cosmic rays, as well as in neutrinos, much more recently as detected by IceCube. So here you can see the galactic plane in neutrinos now from these galactic cosmic rays. So now we have a new experiment, the LASSO experiment, which has opened a new window. So basically the window of PV gamma astronomy. And this, this is, for example, what they see on the sky. So the sky at 25 TeV up to PeV energies. And you can see that the sky is relatively patchy. You see a number of point sources, as well as a number of, well, let's say more or less extended sources, as well as some sources which are extremely extended, as Geminga, for example. So you also now see some traces of hadronic peratrons in our galaxy, with a hint at with a very strong hint at stellar clusters. And you also see a number of these point sources, which are quite likely to be leptonic in nature, so mostly pulsar wind nebulae. And these are interesting for us today in the sense that pulsar wind nebulae have relativistic shocks, and which may be a very good place to accelerate these electrons and positrons that radiate photons at these extreme energies. All right, so this is the cosmic ray spectrum. These these dots on this black line there. And so basically up to the knee, as I was saying, we think that they have a galactic origin, and somewhere at least above the ankle, there should be extragalactic in origin. Somewhere in between, there should be a transition. And the maximum energy of 10 to the 20 electron volts is quite amazing in the sense that this is a macroscopic energy, all contained, so several dozens of joules, all contained in a subatomic particle. So more precisely, well, personally, I believe that the transition occurs more around the second knee, because if you look at Auger composition and at the composition measured by Auger for the cosmic ray spectrum below the ankle, as well as the upper limit, limits on the cosmic ray anisotropy in that region, around 10 to the 18 electron volts, it looks like 10 to the 18 electron volts cosmic rays cannot have a galactic origin, at least not for any reasonable or standard galactic magnetic field model. So it's quite likely that the transition occurs at somewhat lower energies, somewhere there. And for these extragalactic cosmic rays, you need to have to call for the most extreme accelerators, and two very good candidates, which people have been thinking about for a very long time, are active galactic nuclei. So, for example, like CDY, or gamma ray bursts. So here I show short gamma ray bursts, but long gamma ray bursts are also quite good candidates. So you can see this on, for example, by just checking where the sources are in this HELAS plot. So B field versus typical size of the accelerator. As noted at the time, well, basically a source cannot accelerate particles if the gyration radius is bigger than the source size. So this basically means that you have only a very few categories of sources that are able to produce the extreme high energy end of the cosmic ray spectrum. So basically these ultra high energy cosmic rays that we see up to 10 to the 20 electron volts. So you just have a few candidates, and noteworthy ones are basically AGNs and gamma ray bursts. And in AGNs, for example, you can see that the hotspots of AGNs are located here in this region with this red spot in this plot, satisfy the HELAS criterion for, if you plug in typically, well, a dozen of microgauss in magnetic field strength and typical sizes for the hotspots of 10 kiloparsec. Well, you see that in principle, you can confine protons up to about to around 10 to the 20 electron volts in these hotspots. So this means that this could be a site of particle acceleration in these AGN lobes. But this doesn't mean that particles accelerated there. So you need to see whether there is an accelerator, for example, a shock, which is able to do this. So now if you look, for example, this is an image of Cygnus A in radio. So here in the center, the core is basically the supermassive black hole driving all these jets. So you can see here the jets on both sides. And these jets terminate and inflate these lobes, and you can see hot spots in these lobes. So this is in radio. But now if you look in another wavelength, so if you look at higher energies, you look, for example, in X-rays, in the keV range image from Chandra. So here you can see, again, this is the supermassive black hole region here in the center. Here are the jets on both sides. And here at the end, quite interestingly, you can see that there are some very bright spots in X-rays. These are hot spots there, which are basically located in these end regions around the lobes. So this means So since these are very energetic electrons, this time in X-rays, they would cool very rapidly. So these particles must have been accelerated in situ. They must be accelerated locally. So this means that towards the end of the jets, you do have some particle acceleration happening locally. So this is not something occurring much earlier in the jet or close to the supermassive black hole. So it has to happen towards the termination region of the jet. And quite also another interesting point to note is that actually it looks like, so I'm not going to go too far or try to overinterpret this, but it looks like a similar mechanism might in principle happen for microquasars in particular, but this time here, you can see a multi-wavelength image of SS433, quite famous microquasar. And here, the hard X-rays, this bluish color, you can see spots at the regions where the actual jets terminate. So the jets of SS433 are not relativistic, but still, it's quite striking that this looks a bit similar in that sense for particle acceleration. So these two regions are regions of where electrons have been freshly accelerated to very high energies. And this source has also been detected by Hess and Hawke. And this implies in situ particle acceleration, again, in that case to energies above 100 TeV. So this is a very recent paper, as you've seen, published by Hess collaboration in Science, where here they show the gamma emission coming from these regions at the end of these jets. And here, this is just on the right-hand side, this is some schematic picture of what the scenario could be for this particle acceleration. And you could see that in principle here, at the end of the jet, you could have, therefore, termination shock before the fluid flow, the fluid coming from the jets inflates these lobes. And there you may have, then you could have particle acceleration, and all the observations are consistent with particles accelerated in these two regions, the shock region, and cooling while being advected downstream of these shocks, so on these two sides away from the shock. All right, so now to get back to our AGNs. So this is again just a schematic picture of what things may look like in FR2 galaxy. So here you have on the left-hand side, you can see a schematic plot of the jet, a relativistic jet, coming, for example, with a Lorentz factor of the order of 10, coming from the supermassive black hole down there, and terminating here in this region at a shock. And then the fluid flow goes like that. It inflates the lobes, and you should have also backflow around the jet. So on the right-hand side, this is again the image in radio, and you can see this lobe in this region with this typical magnetic field strength, these typical sizes, and the typical magnetization defined as this. In this way, the typical magnetization in this region is somewhat around 1 or a bit below. So in the following, we'll do the simulation for this, our simulations for this type of magnetizations. So one thing to note is that the magnetic field geometry, you can see this, this is plotted schematically with these blue loops here, like this. So in practice, well, the magnetic field is probably more like a helix instead of loops like this, but it does not really matter, as we are going to see a bit later. So just to start with something, we start with this magnetic field configuration. And you see that with this magnetic field configuration, you can see that this is a perpendicular shock. So perpendicular means that the B field is perpendicular to the shock normal. So in other words, the magnetic field is parallel to the shock surface. And we know that for relativistic shock, that's really bad for particle acceleration. So if you have a relativistic shock, so here you assume that you have a relativistic fluid flow coming from the left-hand side and terminating here at this vertical black line, which shows the position of the shock. And then the fluid flow continues towards the right hand, towards the right side at a non-relativistic speed, so typically a fraction of the speed of light, so c/3 if magnetic fields are not dynamically important. So here, this is just a test particle simulation. This is one particle integrated, for example, one proton in that case, integrated from the moment when it crosses the shock. And you can see that this proton has been scattered by the turbulent magnetic fields that I've put in this simulation. It's been scattered back into the upstream of the shock. So again, in the part with the relativistic flow, and then back again into the downstream where it's advected. So basically, if the particle crosses and recrosses the shock, many times it can gain quite large amount of energy. So here in this specific example, it does only one cycle, but this particle effectively gains energy. So the important point here that I've just said is that you should have some turbulence here that I've put by hand in the downstream. And we know that you would get in that case, and we verify this numerically too, an e to the minus 2.2 spectrum in case cosmic rays are scattered isotropically. So this is for ultra-relativistic shocks with a Lorentz factor much greater than 1. But unfortunately for us, or fortunately because this forces us to think beyond this, this is a perpendicular shock that we are dealing with, an ultra-relativistic perpendicular shock. So if you want to think about this in a quite naive way, so, well, we're going to show you more realistic simulations afterwards, but here, if you think about this in a very simple way, so you can assume that you have the magnetic field which is pointing towards you, so perpendicular to your screen, and you have a particle coming in the relativistic flow on the left-hand side, so the upstream of the shock. And then here I plot its trajectory without any turbulence, just this strong magnetic field which is parallel to the shock surface, as is expected at the termination shock of AGN jets. So you can see that the particle gyrates along its magnetic field line, and since the magnetic field line is advected downstream at this sizable velocity of c/3, well, the particle basically follows this trajectory shown in red, and you see that unfortunately for the particle and particle acceleration, the particle is not able to recross the shock. So you have basically no particle acceleration. So the first order Fermi mechanism should not work for an ultra-relativistic perpendicular shock. So in other words, well, the termination shock of the AGN jets should not be able to accelerate the particles that you saw radiating in X-rays strongly in these lobes detected by Chandra in some AGNs. So this is a little bit problematic for explaining particle acceleration with this first order Fermi mechanism. So we need to think of other ways. All right, and this is just to show you. So of course, this test particle simulation is a bit simplistic, oversimplified. So of course, there is a wealth of literature on this. Lots of groups have made very interesting particle in cell simulations, which are of course much closer to reality than this simple picture that I've shown you. So for example, in the unmagnetized case, so these are, for example, some simulations from Anatoly Spitkovsky or Lorenzo Cironi, where they see a non-thermal tail developing in the unmagnetized case. So these are good particle accelerators, although they are very slow and also would not accelerate particles to very high energies. So you see here, for example, in this peak simulation down there, you can see the magnetic field, and here in the shock region, here you can see clearly viable filaments from the viable instability mediating this collision-less shock. Now, in the magnetized case, actually it's not. It's even worse, in the sense that the particle acceleration is very rapidly quenched. So Emax quite quickly saturates, which basically confirms the fact that you should not be able to accelerate particles at these shocks. So what is the solution? So one thing we noted is that all these results are for plane parallel homogeneous shocks. And in nature, so it's always good to simplify the problem to these basic ingredients. But of course, in nature, you have large-scale magnetic fields. The geometry of the large-scale magnetic field is more complicated than that. And of course, any astrophysical shock will never be truly plane parallel or truly homogeneous. And what we suggest and what we notice from our work is that the large-scale geometry of the magnetic field can actually, if it's taken properly into account, it would actually help very strongly to get particle acceleration, and you can get very efficient particle acceleration. So one thing to note with the large-scale geometry of the magnetic field is that in the case of a jet like this, you have a null point for the magnetic field in this magenta line in the center of the jet. So basically the magnetic field should vanish in the center, really in the core of the jet. And if you think about, how the magnetic field direction would look like from one side to another of this central line here in magenta on this plot, well, you can see that if you look on one side, the magnetic field would be pointing in one direction, always perpendicular to your screen. And on the other side, it would be pointing exactly in the opposite direction, but again, perpendicular to your screen. And this geometry really helps for particle acceleration. Actually, it's very reminiscent to previous work that we did with John Kirk for pulsar wind nebulae, where we showed that the large-scale geometry of the magnetic field close to the equatorial plane and close to the termination shock of pulsar winds would allow for one sign of charge, either electrons or positrons, to be accelerated at the termination shock, although this shock is again a perpendicular ultra-relativistic shock. So in that sense, we found that the geometry of the magnetic field, so for example, here in that case, you have the pulsar in the center surrounded with a radial ultra-relativistic wind going in all directions around the pulsar. This green arrow is the magnetic axis of the pulsar, and it opens an angle with this angle. It opens a region, the region of the striped wind around the equatorial plane with an angle theta, with the angle theta being the angle between the magnetic axis and the rotation axis of the pulsar. And this relativistic wind around the pulsar terminates here at this blue line on this schematic plot, corresponding to the termination shock of the pulsar wind. And this is, in this region, so the equatorial plane for the rotation of the pulsar is this plane which is perpendicular to the rotation axis and going through the pulsar. In this region, which is basic, so in 3D, you should see this region more like a donut-shaped region all around the pulsar. So basically the intersection of this plane with the termination shock looking more like a sphere. So in this region, you get very strong particle acceleration in our simulations, because in this region, the magnetic field also flips. So the magnetic field vanishes along the equatorial plane. So again, you have a null point, a null region. In that case, it's not just a line, but it's more a plane. And the magnetic field, for example, here is pointing towards you above this plane, both in the upstream and in the downstream of the termination shock. And here below this plane, it's pointing in exactly the opposite direction, although in both cases, it's still perpendicular to the screen, to your screen. So the point is that the particles spend some time on these so-called Spicer orbits, because the Lorentz force, if the sign of the charge of the particle is the right one, it pushes the particle again towards this plane here in the center, this equatorial plane. And this is good because we also expect stronger turbulence levels in this region here around the equatorial plane, just in the current sheet, downstream of the termination shock. So more particle scattering there. And therefore, if the particle is well confined in this region, you can have a very efficient particle acceleration. So this is what our test particle simulations of 2018 showed. So here in blue, you can see the trajectories of successful particles that have been able to gain energy by crossing and recrossing the shock by doing at least one cycle. So the shock is this dashed vertical line. Again, the upstream is on the left-hand side with the flow coming relativistically from the left and flowing towards the right-hand side. And the equatorial plane, where the magnetic field direction flips, is basically here at z equals 0 in this horizontal line in the center, horizontal region in the center. So on the right, left-hand side, it's for one sign of charge, here positrons, that have not been accelerated efficiently because shock drifts kicks them out from that region. But for the other sign of charge, shock drift keeps them in this region, as I was saying, on spice orbits. And you do have very efficient particle acceleration in this region, because you see that the particle crosses and recrosses many times the shock in this region. So very efficient acceleration of one sign of charge. So what we think is that this can be applied also to the case of AG and jet termination shocks. So this is a very interesting work from Jiao Huang. So I think you may hear a little bit more about it in a couple of weeks in Brian Reville's talk, but I'm not going to talk much about it. But the idea is also that, so this is for the particle acceleration around a termination shock for a relativistic jet 2. And you can see that here on the left-hand side, particle trajectories, and you can see quite clearly that one sign of charge is remaining around, is oscillating in a somewhat more complicated trajectories around the central axis of this jet. And the idea is somewhat similar to what I was showing you before. The Lorentz force is always pushing back that good sign of charge towards the center of the jet, allowing them to remain focused in this central region of the termination shock of the jet, allowing it to be accelerated to very high energies. And indeed, in his simulations, you can see that particles of that correct sign of charge here, this yellow line in the right-hand plot, you can see a very hard particle spectrum extended to high energies, and that shows you that you get very efficient particle acceleration. So now the question is, what happens if you do not do these calculations in the test particle limit? What happens if you do it by taking into account the back reaction of the particles? Because if you have lots of particles that accelerated and you have lots of relativistic particles in the central region of this termination shock, just around the null point in the middle zone of your jet, in the core of your jet, then if these particles have a large pressure, you would expect that the test particle calculations would start not to predict you exactly the correct results. Although, I mean, the idea that will remain, as we're going to see, is that these high energy particles remain on spice orbits and remain well confined in the central region of the jet. But now we need to see by doing this with particle in cell simulations, so peak simulations. So these are simulations done with the Z-drone code, so from Benoit Serretti. So this is a simulation that we did, a peak simulation in a 2D Cartesian box in a XZ plane, shown here with this box. Here in red, these are reflecting boundaries, which are basically, so on the upper part, so here this plot here in the center shows you a schematic drawing of what we do in our simulations. So basically, we have this rectangle is the box of our simulation. We inject particles on the left-hand side at relativistic velocities, so at relativistic speeds. We inject them with a Lorentz factor of gamma equals 10, and we let them flow. So we inject electrons and protons, which are wrote here as ions, but these are protons in the simulation. So electrons and protons flowing at gamma equals 10 from the left to the right-hand side. The red lines are basically walls. So these are reflecting boundaries. So here on the upper and lower walls basically mimic the external confining medium around the jet, whereas the wall on the right-hand side here at the end is basically there to mimic somehow the contact discontinuity. So in other words, if you once you smash the fluid coming from the left onto this wall, what is going to happen is that you're going to create in the simulation a shock, which is going to move, which is going to be created very close to this wall, and which is then at later times going to move from the right-hand side to the left-hand side like this, moving from the right again to the left. And in this way, we can simulate basically this termination shock. So if you just follow what happens in the rest frame of the termination shock, you have a good idea of what should be happening in the termination shock of your AGN termination jet. So here is for the magnetic field configuration. What we do, we put a magnetic field like shown with this blue arrow. So blue, for example, we put the magnetic field pointing, so perpendicular to the screen always, but pointing towards you below this null point with this dashed magenta line in the center, and entering inside your screen in the exact opposite direction in the other side of this null point. And the region between these dashed lines in black is basically the region where the magnetic field vanishes, which is basically the external medium around the jet. And the central region in the simulation is the jet. So here I show you the B field profile as well as the current profile. And here, just to give you an idea, so basically these simulations are quite massive because you have more than 100,000 cells in the X direction, and which corresponds to something like more than 6,000 ion skin depths in this X direction, and in the Z direction, so perpendicular to the jet, you have 410 ion skin depths. All right, so this is these are the results of this simulation. So again, this is the box, so blue. So these are the results for the density of the fluid. Blue means lower densities and red means higher densities. So you can see here, for example, around 6,400 in the first upper plot at early times. You can see here this region, which corresponds to the region where this relativistic shock is formed in the numerical simulation. Again, the region, okay, which I called Z, but here in practice, here I just call it Y on this plot. Never mind, you get the idea. So here, Y equals 0 represents the central axis of the jet, so the region where you have this null point for the magnetic field. And here you see the shock is propagating from the right-hand side to the left-hand side in the numerical simulation. So here at later times, the medium panel, you can see that the shock is somewhere around between 5,800 and 6,000. So somewhere here, if you can see the mouse, the cursor of my mouse. And here it's a bit further away. Again, it's around, at again later times, it's around 5,600 there that you have this shock. So of course, in the shock region, the magnetic field is, the fluid is compressed, and that's why you go from blue to red. So this is why you have this discontinuity in the fluid density. But an interesting feature that you did not see in any other simulations, and in particular in these plane parallel homogeneous peak simulations, here you can see on top of the shock, you can see a weird low density cavity forming around Y equals 0, just ahead of the shock in the shock precursor region, and just basically corresponding to the central region of the of your AGN jet. And you see that this cavity grows with time. So the cavity which was here is now becoming much bigger and even bigger. And at some time it starts to saturate and reach, once the width of this cavity reaches the width of the jet. So in our simulations, the jet is basically, the jet width is around 100 here in these units in ion skin depths. So here between -100 and +100 is basically the width of the jet that we inject in the simulation. You can see that the cavity saturates. So we run the simulation long enough to see that it does saturate there. So I'm just going to show you a movie of of how this looks like. All right, so this is a movie of this for the density. So you can see the cavity forming here. And behind the cavity, you can see that there are some blobs, some bubbles, some vortices detaching from behind the cavity. And you see a nice alley of vortices forming just behind this cavity. So I just replay it again. So here we smash the fluid coming from the left-hand side to the right-hand side. We smash it on the wall on the right-hand side, and you can see the shock propagating towards the left-hand side. And this cavity forming, growing, and now the cavity saturates. It has reached its maximum size. And now you see just behind it, really some microscopic fluid phenomenon just behind it. So full screen. And this is known as a von Karman vortex street. So this is a well-known fluid phenomenon where you see these vortices. For example, when you have an obstacle and you see behind the obstacle the fluid flow going, for example, from the left to the right-hand side here. When you have an obstacle formed by this cavity, you have these vortices behind, which is called the von Karman vortex street. So it's quite interesting in the sense that our simulation is not a fluid simulation, it's a peak simulation, but you do see very clearly the fluid, the particles behaving like a fluid. So now if you look at so the upper panel here is the density in our simulations. Now if you look at the magnetic field, so as I said before, so blue means for example, pointing inside your screen, so again perpendicular to the screen. The null point here in white means weak magnetic field, so weak magnetic fields inside the cavity. So this corresponds to the cavity. The white region here for the magnetic field is the region of low density in the fluid. And red means magnetic field pointing in the opposite direction, for example, towards you. And here you can see that the fluid goes around the cavity and then more turbulent in the downstream. So here I'll get back to the plot for the velocity, but you do see that you have a very strong velocity shear on the edges of the cavity. But quite much more interestingly is where you have all the high energy particles. So we looked at where is the cosmic ray pressure. What is the cosmic ray pressure? So here we looked at the average mean Lorentz factor of the particles in the simulation. And we see here in yellow, this means that you have very energetic particles. All the very energetic particles are confined in this cavity. So basically it's low density, but very large cosmic ray pressure. So that's where all your cosmic rays, and especially the high energy cosmic rays, are located. And some of them leave behind in these vortices, in the von Karman vortex street, just behind this, just behind the shock. So basically what you see in these simulations is not only particle acceleration around the cavity, but you even see also particle escape. And you can even see also how they escape. You see that actually they escape in these vortices that you just saw before. The cosmic rays remaining confined in these vortices and being probably later released in the environment. All right, so this is the ion spectrum that we get from our peak simulation. So this bump at gamma equals 10 is basically the Lorentz factor of the injected particles in the relativistic relativistic jet, sorry. And here, this very long non-thermal tail that extends for more than 2 orders of magnitude in our simulations is basically shows you the particle, the cosmic ray spectrum in the simulation. So this is the spectrum for the protons in our peak simulations. You see that actually the spectrum slope is close to minus 2.2. I'm not entirely sure whether it's a coincidence, but it's quite interesting to note this. And here there is a cutoff, which is not due to our simulations not running long enough, because we run them until this cutoff saturates. So here, these colors show from blue to red the time evolution of our spectrum. And here you can see that at the very end, the spectrum starts to tends to saturate to this final shape, this very dark red shape here. So this does not grow beyond this. And it's interesting to note that the actual HELAS limit in our peak simulations should be around gamma equals 1000 here. And you see that the cutoff that we see in the proton spectrum in our simulations actually coincides with this HELAS limit. So we reach the maximum theoretical limit in these simulations. And this is just the evolution, just to show you the same thing, but the evolution for the maximum particle energy, this blue line on this, looking at this gamma on the left axis, the maximum particle energy in our simulation versus the width of the cavity that we calculate with these red dots. And you can see that they both grow in the same way. So basically, this is due to the fact that the width of the cavity is basically corresponds to the gyration radius of the highest energy particles in the system in this simulation. And in the end, the width of the cavity as well as the maximum particle energy in this peak simulation saturates around this Hillas criterion limit, as expected from naively. So now how are particles accelerated? So actually it's not standard particle, not standard shock acceleration here. It's a little bit more unusual in the sense that the particles indeed they are accelerated in the shock region, but they're not quite accelerated at the shock front. Actually, the acceleration mechanism that we see in our peak simulation is much closer, is actually much closer to proper shear flow acceleration. And this shear flow acceleration occurs at the edges of this cavity where all the very high energy particles are confined. So if you look at the velocity of the fluid, so this is the velocity in the rest frame of the wall on the right-hand side, so basically the observer rest frame. Here magenta means that it's moving towards the left, and green means that it's moving fast towards the right-hand side. So here, on the left-hand side, so the shock region is somewhere here, just at the just around the cavity at the end, rear end of the cavity. And here you can see clearly here you can see the fluid flow going around the cavity at very large velocities with a gamma around 10. And inside the cavity, the fluid is actually, you have a strong backflow. The fluid is going in the opposite direction in this rest frame. Well, of course, in practice, if you put yourself in the rest frame of the shock, you would not see the flow moving ahead of the shock. It would move with the shock. But basically, you have a very strong, the important point to note is that you have a very strong shear flow at the edges of the cavity just because of that. So basically, in the shock rest frame, the fluid inside the cavity is not moving much, it's quite stationary, but you have a very strong, when a particle manages to cross the edge of this cavity, it would feel a very strong change in the fluid velocity because you have the fluid from the upstream coming with this gamma equals 10 in the simulation. So now if you look at the ideal motion electric field in the lab frame, it would look like this. So if you plot minus V cross B in this simulation, you would see this, which means that you have very strong electric fields here on the edges of the cavity, and with this white spot here in the center that you can see here, corresponding to the cavity. All right, so when the particle crosses and recrosses these regions, it gets a very strong boost in terms of particle energy. And here, for example, here you can see a few particle trajectories which have been selected. These are the particles plotted like this. So the cavities this time you can see down there. The shaded region correspond to the density of the fluid in the simulation, and these lines, these colored lines on the left-hand side panels correspond to the particle trajectory. Red colors mean higher energy, so the particle is starting in the blue parts on the upper parts of these plots, with a small Lorentz factor, and they have gained quite a massive amount of energy because they all have been boosted around a Lorentz factor of 1,000 in all these for these 4 particles. So here red meaning the end point of the particle in the particle trajectory in these simulations. So what happens is that you see that the particle is playing around this null point. The null point is now vertical on these simulations. The particle is oscillating around this null point for the reasons that I've already explained before. And these big, bigger field circles in color that you can see on these trajectories correspond to basically big circles means that the particle is experiencing large acceleration in these regions. So basically you can see that the acceleration happens in quite brutally in very distinctive, in only a few places in the simulation. So it happens, for example, here. Oops, sorry. For example, here, then again here a sharp acceleration moment here, 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 and here. And we see that each time that the particle is accelerated strongly, that basically corresponds to the moment when the particle experiences this strong shear flow and crosses just the edges of the cavity. So we can see the same thing by plotting on the right-hand side, the evolution of the Lorentz factor of these 4 particles. And you can see that it just goes up by steps. For example, the first one is extremely clear. It's almost a textbook example. You can see 1, 2, and then 3, and then a smaller 4th step in which the particle is increasing its energy, and they all correspond to the moment when the particle is crossing the edges of this cavity. So for example, we can see this in a simulation. So here I'm going to show you one simulation. So here, down there, it's the Lorentz factor of that particle, which is going to increase. So now it's increasing energy. You can see where it is with respect to the cavity. So the cavity is here in the center. And if you look closely, so the particle, as you can see, it oscillates around, the particle oscillates around this null point for the magnetic field, again in the simulation, as initially forecasted. So now the particle crosses the edge, gains energy again here, and again here a small increase in energy at the end. So you can see that the particle in this simulation gains all its energy at each of these crossings. So here one more time, again crossing here, here, and the last one. So, all right, so now also one remark on the potential effect of the poloidal field component. If you have not just a B phi, but also BZ component, well, the results do not change much unless the Z component becomes too strong. So what we find, we tried different strengths of this component. So here, for example, I show the density for different strengths of this component from 0 up to 10% of the B phi component. And you can see that you still form a cavity, you still have a cavity even with BZ being non-negligible. And on the right-hand side, you can see also the particle spectra in our simulations for these different strengths of this poloidal magnetic field component. And you can see that even with 10%, BZ equals 10% of the magnetic field strength, you still get a very high energy particle tail. So the magnetic field, this part of the, sorry. So if the magnetic field is helical, as long as the helix is not too loose, you would still expect this mechanism to work. Now, regarding particle escape, we also verified that the particles that escape in these von Karman vortex-free Halley vortices, that these particles do not suffer any sizable energy loss. So we plotted the particle spectra on these, for example, in one of these vortices, here shown in blue, in this box, black box on these 3 panels at 3 different times, representing later times in the simulation. And you can see, for example, the green one is not, the tail is not substantially cooled. So we hope from this that indeed the particles that have been accelerated in this cavity from this mechanism are indeed able to escape in the environment without suffering major energy losses, as it should be the case if you want them to be, if you want this mechanism to be responsible for the ultra-energy cosmic rays that are detected at Earth. All right, so how would you find, how could you prove this observationally, this theory? Well, one possibility that we suggest is to look for traces of this cavity. And we think that this cavity could appear as an underluminous hole in, for example, in an X-ray map, in a synchrotron map of an AGN. So if you look, for example, this image that I've already shown you before, in this case, it seems that you have such a hole here in this region. There is a surprising hole, which has, as far as I know, no very clear explanation in X-rays here, shown here. So this inset is an enlargement of this region. which is close to the region where you would expect a termination shock, at the end of this jet, relativistic jet. And this hole may be maybe the first signature of such a mechanism occurring in this region. So I do encourage observers to look for possible for such possible cavities and see whether this would fit with our theory. So this would be quite interesting. So the reason why you would have such a hole in the synchrotron emission is relatively easy to understand, in the sense that if you look at our simulations, the magnetic field strength inside the cavity is pretty small, whereas it's very large just around the cavity. So what you would have is that the region from the cavity would not radiate much in synchrotron, and therefore would appear like a hole in your synchrotron map. All right, so in this case, in this Chandra image, it's quite interesting because this might be one of the first traces that we have. So some conclusions and perspectives on this particle acceleration at AGN jet termination shocks is that, so what we have found is that the large-scale structure of the magnetic fields is actually key for having particle acceleration. So without it, indeed, if you just have a plain parallel homogeneous perpendicular shock with an ultra-relativistic outflow, you would not expect particle acceleration. But as soon as you take a more realistic geometry for the magnetic field, just basically as you would expect in any such jets, you would start to see particle acceleration as shown in these peak simulations. And particle acceleration is actually very efficient and can even reach without any problem the HELAS criterion. At least the HELAS criterion in our peak simulations, obviously. Whether the HELAS criterion is reached in a real astrophysical jet, where you expect to have particles accelerated by something like 10 orders of magnitude in energy, is of course another question which cannot be addressed in a completely clear way by peak simulations. All right, so this mechanism is much more generic than what I've shown here. So this could also apply for microquasars as SS433, as I was saying before, but this may also apply for gamma ray bursts, because they also have jets with, in principle, such a magnetic field topology, whether you have protons or rather electrons and positrons is another question, but this would also work for electrons and positrons. And this also works, as I've shown before earlier in my talk, for pulsar wave nebulae, in pulsar wave nebulae, and basically electron and positron acceleration in these objects. So basically the geometry is a bit different, because this time it's not just a null point looking like a line, but it's a null point in the B field looking like a plane, basically corresponding to the equatorial plane for the rotation of the pulsar. But this is exactly the same idea. And we also did some peak simulations with electrons and positrons, this time without protons, and for a configuration of the magnetic field more relevant for pulsar wave nebulae. And we do see the same mechanism occurring there for electrons or positrons. So what we saw for these, is that we do reach for these peak simulations for AGN jets, we do get a cosmic ray dominated cavity, so a cavity with a low density of fluid, but a strong cosmic ray pressure at the shock front around this magnetic field null point. And this may be visible in synchrotron images if you look for such cavities in synchrotron images of AGNs and AGN lobes. So for particles, the particles, they are not accelerated at the shock front per se, but they're accelerated at the strong shear flows that are present around this cavity. And as I was saying earlier, they are accelerated to the HELAS limit in the simulations. So this means that this is very promising for accelerating particles by this mechanism at AGN jet termination shocks up to ultra high energies, if you rescale our results to the length scales and magnetic field strengths that you would expect for real life AGN jet termination shocks. And you would expect, for example, for microquasars, so for example, for SS433, you should expect that you can reach also PV energies by the same mechanism for this kind of environments. And also we find in these simulations, we can also, another point, in addition to being able to reach the HELAS limit in the simulation, another noteworthy point is that we're also able to address the question of cosmic ray escape. And we do show, we find something new in this, the particles are basically advected in the von Karman vortices, just in the downstream of the shock, just behind this cavity. And they live there without substantial energy loss in the simulations. So, and so now the last point that I would just like to address is, well, of course, peak simulations are quite limited in terms of scales that you can reach. And one, well, alternative way between one alternative method that we need to, that we want to study and that we have started to study right now for the next step is basically between the two extreme simulations that I've shown. So on the one hand, I've shown you peak simulations, and on the other hand, I've also shown you, in the case of pulsar wind nebulae, I've also shown you some test particle simulations. But we want to do this in somewhat intermediate way with peak MHD simulations. So in that case, you cannot resolve in a fully self-consistent way particle acceleration, obviously, but you can simulate better a jet as well as a termination shock as a jet termination shock in the simulations than in a pure peak simulation. And the other interesting thing to check with peak MHD simulations is how high in energy you can also get the particles going in this scenario. So this will be for future works and hopefully interesting new results in this direction. So I think there is here a new mechanism for particle acceleration at relativistic shocks, which has not been discussed much in the literature before. But I think the pace is gathering in this direction, and I think it's an interesting direction of study that I encourage you to think about, because there is much more work to be done in this direction, and this might solve or at least provide a viable answer to one big open question in theory as to how you accelerate particles to extreme energies, and especially how can you do this with ultra-relativistic shocks with a perpendicular magnetic field, perpendicular ultra-relativistic shocks, which in principle should not have been able to accelerate particles. All right, so thank you very much for your attention, and I'm going to stop on this slide.
Thank you, Gwenael. That was really excellent. Great to get that overview. You have a few questions. Let's start with Maxime.
Hello. Thanks for very interesting talk. I have one comment to your work. It could make your life a little bit worse, but not terribly worse. It's about structure of jets.
Maxime,
yes.
think we should postpone this to the discussion part. Maybe we'll finish with questions now, and after that to have a long comments, because this is the structure of the seminars. I think let's finish with the short questions, and then after that you could comment.
Okay.
Yeah. Okay.
All right, so we'll take Maxime's question later. So let's focus first on the seminar itself. So Evgeny, you want to go ahead? You're muted, Evgeny.
Oh, sorry. Thank you for the talk. I have actually 3 questions, and all of them are related to the geometry, which I probably didn't understand very well. First question is, do I understand correctly that the leading cavity is propagating with essentially with velocity of light, with gamma equal to 10 from the central engine?
Well, it's propagating from it remains at the shock surface.
Yes, but does it propagate from the central engine at the speed of light? This was my understanding. If you send the jet,
it's not from this. I mean, the termination shock looks like a standing shock in the rest frame of the observer. I mean, what you get is relativistic flow coming from the central engine on one side, and that terminates. So the shock looks like a standing shock. It's not propagating with respect to the central engine making these shocks.
Okay.
It's with respect to the fluid in the upstream.
Okay. Then the second question is regarding the von Karman street, as you showed us. It looks like it completely disrupts the jet structure. At least in your simulations, I cannot see a jet anymore. I only see these vortices. But in reality, we see the jets. Why?
Yeah, okay. So the von Karman vortex street lane is behind the jet, behind the shock. So the jet is on the other side of this. So the jet is on this left-hand side. So it's not quite easy to see it in the simulation, but I can tell you, well, because it's made with a peak simulation, so you have to do what you can do in peaks with a peak simulation for jet. But what you have here is the jet is in between this minus 100 and plus 100 in the y-axis. So what is true indeed, and that's a very good question, and I also hope that we'll get more understanding of this by doing peak MHD simulations. What is indeed true is that the size of the cavity grows to the size of the jet, basically. I mean, similar to the jet size, as you can see here. So it does start to have a disruptive effect on the fluid flow very close to this termination shock. So this is just in the region of the termination shock. So it does not disrupt anything for the AGN jet itself. But at the very end of the jet, yes, the jet is somewhat affected in that the fluid flow is forced to go around this overpressured cavity.
Okay. And the final question is, do I understand correctly that in the simulations, your jet is cylindrical? It's not conical, it's cylindrical.
Sorry, I didn't quite hear.
Is the jet cylindrical or conical in the simulations?
With this magnetic field geometry, I mean, we did have to do, okay, so this is indeed a limitation. So we had to do the numerical simulations in 2D, given already the sheer size of these simulations. So doing
yes, but in 2D you can do conical as well. This is why I'm asking. Is it conical or cylindrical?
Yeah, so here you have the B field, sorry. You have the B field conical, yeah.
So the jet is conical, it becomes wider if you go away from the central engine. Is it correct?
I'm not sure in what sense you mean this. I mean, these peak simulations cannot address any widening of the jet, right? You mean widening in what part?
Okay, then let me go a little bit deeper into the reasoning why I'm asking this question. As we know, especially in gamma ray burst or in AGNs as well, the jets are usually either have angular width of 1/gamma or even wider. In this sense, the opposite sides of the jet, the right side and the left side, they are not causally connected actually. So the particle in reality cannot really travel across the jet. And it looks like in your simulations, the jet is causally connected, the whole jet is causally connected. And this in principle, if I understand correctly the setup of the simulations, then this in principle can influence the results.
Right, I mean, I guess maybe we should discuss this in more detail later. I'm not entirely sure I fully got your whole point.
Yeah, let's come back to this question. Thank you. Let's take a question from Michelle.
Thanks, Gwenael. Really interesting talk. I was wondering about this cavity that is formed, and about speculations about what would be the origin, what would create such type of cavity? Would it be? Do you have ideas of given plasma instabilities that are excited along the time of the formation of such cavity, and so on, to explain at the beginning why this is actually depleting? And afterwards, obviously, getting all the trapping the accelerated particles.
Yes, so I mean, basically, this cavity is basically due to the strong cosmic ray pressure itself. The strong pressure basically forces the fluid flow to flow around this cavity. So these cosmic rays remain in this region thanks to the magnetic field geometry with these spice orbits, so the particles moving around this null point in the center. And this very strong pressure of the cosmic rays basically forces the fluid flow to go around it, and therefore excavates this cavity in the fluid in the immediate upstream of this in these simulations.
And after how many ion cycles do you start seeing clear formation of the cavity? So basically getting a sense of when the cosmic ray pressure has exercised enough work for it?
Well, you can see this quite clearly in these simulations. So let me see if I can stop it. Okay, so this is, oops. All right. So here you can see that it occurs very, very quickly. So here you already see a very small cavity for omega PIT or the order of a few hundreds there, and even a bit before.
Okay. Okay, thanks.
Thanks, go ahead.
Hi, Gwenael. My question is about your statement that you can see end of the spectrum close to the Hillas, comes from the Hillas condition. Question is that effectively implies that electric field is very large, comparable to magnetic field. So do you follow the electric field in these simulations? So could you pick, so they are clustered, there are islands of electric field, or more or less distributed homogeneously?
Okay, so if you look at the ideal motion electric field, so here on this plot you see the
This is the B
magnetic
field, right? This is B
yes.
field.
Yes, this is the B field.
So electric field simply follows the B field?
So here the electric field. So here, if you plot the ideal motion electric field, I mean, it shall be this the minus V cross B, in which case you can see that the region with the strongest fields are just around the cavity like this. These are very red regions that correspond to the regions just around the edges of the cavity being this white hole in the middle, where the E fields are close to zero.
And they are stable. This electric field is stable. Just I'm asking this because I remember there are some peak simulations by Cironi. They are showing some very strong electric field, which was nevertheless not stable. Just do you see the same in your simulations?
I mean, what we see in this simulation is that the cavity remains stable once it reaches its maximum size. I mean, of course, it's propagating, but it's once it reaches its maximum size, it remains well, basically like this. You just see vortices detaching behind it, but that's all.
So acceleration takes place just closer to this part.
Yes, just close to the edges of this cavity.
Mm-hmm. Okay, thanks.
Other questions? Felix, I think we can open this up to general discussions at this point if there are no other questions specific to
Yeah.
the talk.
Then we go to Maxime. Long comment, I say, scared us. Maxime? Oh,
Maxime is muted.
Yes, I'm here. I just have a short comment about structure of jets. In your initial, can you hear me?
Yes.
Yes, very
Okay.
well.
So in your picture, you have a 0 point at axis of a jet.
Yes.
And as I understand, you use mainly only toroidal field. But
Yes. Yes.
jets, especially on a very developed stage, have a very strong, very developed core with strong poloidal field, which much stronger than toroidal field in the rest of jets. So you didn't have clear like a 0 point. You have a point with poloidal field.
Okay.
Not, and it's this core can like a lead keep quite significant part of jet power.
Yes, let me share my screen just to check if this is what you mean. Okay, so here you're talking about this BZ component, right?
Yes.
Yes, so we did some simulations. So I agree that if
no. But you have a BZ component outside. BZ component outside much smaller than toroidal field, but BZ component at the center, at the core of the jet, it's higher than toroidal field. You have very strong, very thin central part.
Well, I mean,
Yeah,
the central. Okay, so in these simulations, I mean, the central part is not so small. I mean, you do have a part in the center where BZ would dominate in that kind of scenario. So basically, I mean, we tested up to these values of BZ over B0 of 10%. I mean, slightly beyond, but here are the simulations.
It can be a much larger than one.
This is okay. So B0, it would correspond rather to really the strongest part of the B phi, farther away from the core of the jet. But in the core of the jet, you would be dominated by BZ, even in this 0.1 case. I mean, the profile, so let me see. Yes, the profile of the B field is like this. And this is in units of B0. So you can see that, okay, so let's say,
But B0 didn't go to 0. And the B0 have same sign in both sides. It didn't change sign. BZ should be the same sign on both sides from left and right.
Right, that's the case, yes.
But what you show, it's like a little bit different.
Sorry, in what sense? So here we have a BZ on top of this B phi.
Could you show like a profile, magnetic field profile in a jet?
Yes, okay, so that's the case with BZ equals 0. So I'm sorry, but I don't have the case with the BZ non-zero. But this is the magnetic profile. So versus, of course, the width of the jet, the width corresponding to these dashed lines there.
BZ looks like more like a Gaussian profile with maximum at the center.
Right. I mean, we can try with the Gaussian profile too. I mean, this has not been done yet, but the idea was.
You can look our paper with Commissar of 2009 or can you hear me? Hello?
We hear you, but I think we may have lost Gwenael.
I see.
Did we lose you? He's kind of frozen. Felix, do you have any additional thoughts regarding Maxime's questions?
Yeah.
I think we may have lost Gwenael. Yeah, he may be rejoining.
Just wait maybe a couple of minutes.
Yeah, let's just wait.
Well, maybe some others could answer to your comment, Maxime, before Gwenael will appear again.
But I think it's this modification should not kill this mechanism, because in any case, acceleration with like a colloidal field, it's allowed. It should be not a big problem in this way. It should be like modification, not like full kill of a model.
Okay, I'm very sorry. I've lost again a part of what you said because my internet connection is not quite stable. So,
Well, we can hear you very clearly
Maxime,
now.
quickly ask question again.
I say what I say. It's not full it's not real problem. It's like a modification of approach which you could try to solve. It's like you have a colloidal field which allows acceleration in a shock. So
okay.
in this way, you have diffusion across the shock zone, but it's simply you can use a initial setup with not zero magnetic field, but some small colloidal field. It's all.
Okay, I see. Very interesting. So this is in the 2009 paper?
2009, Комиссаров, Лохакис, Кёнигл, me, and Beskin, Nohrin, 2006, I think.
2006. Okay. Okay. Okay, well noted. Thank you very much for this, Maxime.
Okay. Thanks.
Okay, that's very interesting.
Any other discussions, questions?
Well, in principle, it's not really related to the talk itself, but to acceleration as such. I just made a quick estimate for the parameters that you gave us, several tens of microgauss magnetic field and the size of 10 kiloparsec or so. And it seems that the converter acceleration will work under these conditions. If it does, then you don't need to invent anything about the magnetic field geometry, because this acceleration mechanism doesn't care about the magnetic field geometry. So maybe it works there. I don't know. The Lorentz factor that you expected to get for this acceleration is 10 to the 6 for the electrons. But of course, you will not accelerate protons in this way. For protons, you may need something different. Maybe even electrons are accelerated in one way and protons are accelerated in a different way. This is, I think, also possible.
Yes, I see. But I mean, our point was to accelerate protons. Our point was to accelerate protons.
Yes, I understand it. But for electrons, we know the result. We know the synchron radiation, etc., etc. What we see is electrons, actually. what we want to get is probably more protons to explain 10 to the 20, but what we see is electrons.
Yes, obviously, yeah.
In this sense, we see one component and want to get another component, and it's not at all clear whether they are accelerated in the same way.
But why you cannot apply? You just estimate from synchrotron the acceleration rate of electrons and then apply to protons.
If they accelerated in the same way, then yes, but how do we know? I mean, they are different. There is a process, the conductor acceleration, which makes them different, really different.
Oh, by the way, this is to continue this question is did you try to calculate synchrotron radiation?
Not in these simulations. I mean, we did peak simulations for pulsar wind termination shocks, for which we calculate the synchrotron radiation. So in that way, yes, but not for this case. But there is actually a very good point, which goes in the direction of what Evgeny just said, which is that.
Sorry, yes, sorry, go ahead.
Yes, which is that our mechanism 2 does discriminate between protons and electrons, in that one sign of charge is accelerated to higher energies than the other one. So in practice, it does seem that you get acceleration in both cases for both signs of charge to sizable energies, but you can have a quite different energy cutoff. So this I showed it very quickly, but I can just re-show it right there. So this is basically what you would see for, so the black dashed line is the electron spectrum at the end of our simulations. And you can see that it's not the same as the proton spectrum. It has a cutoff at
but that is not the losses. Do you take into account there is no losses here? Synchrotron losses in these calculations?
I mean, naturally you would have these, I mean, naturally you have the losses, but the point is more the point shown here. For example, shown here that only one sign of charge is well confined around the center of the jet. Because if you change the sign of charge, then the Lorentz force goes in the opposite direction. And instead of keeping the particles in that region, it actually ejects them. So there is some level of discrimination, at least for the maximum energy, at least for the most extreme particle energies. So I think, yeah, I mean, Evgeny raised a very good point, to which I do not have a very full answer right now in terms of whether, I mean, because we cannot answer this question with a peak simulation, we would need many more orders of magnitude in energy range. But the good question is, if you have a jet which accelerates protons, say, to 10 to the 20 electron volts with this mechanism, are you able to accelerate electrons to sufficiently high energies in this same jet so that they can radiate in X-rays? So this is a question which cannot be answered immediately with such peak simulations, but that's a very important and interesting question too.
Gwenael, I just continue my question. It's just because I understand in this picture, you should not have a continuous X-ray on the scales of kiloparsecs, right? This here, because energy loss of electrons, it should be located in a specific sites at the termination shock, primarily, of course. And so in the Chandra jets, we see, like you showed, one thing is the hotspots, that is probably that works. But along the jet, which goes to kiloparsecs, tens of 100 kiloparsecs, probably this mechanism cannot provide such a continuous.
No, elsewhere it certainly would not function. I mean, this is really a mechanism which is
only at the hotspots.
Yes, yeah, really for the termination, really for the end of the jet.
Yeah, because in that sense, I mean, the shear acceleration mechanism has a big advantage. It's everywhere. It's just...
No, I fully agree. I mean, I mean, it's almost, I mean, I think it's pretty clear that there are several acceleration mechanisms working in different places in AGN. So
but
this is not.
Yeah, independent your work, what do you think? Is any other mechanism to explain this long homogeneous X-ray jets rather than except for shear acceleration mechanism? Because there are some words about that. The what is this? This stochastic acceleration, but that is just words. I mean, stochastic acceleration. While shock, of course, could not explain that, electrons simply will die close to the production site. And then, but shear acceleration does this work just very naturally. So
I'm sorry, I'm going to leave now because I have to join another meeting, but I don't want to interrupt. Please continue. The room is available and you're the host now. I just want to thank Gwenael, really great talk, and thank you for participating. But please continue.
Well, thank you very much for the invitation, Rashmi, and see you next
See you
time.
in 2 weeks. Yes. Continue, please.
Yes.
Sorry for the interruption.
So Gwenael, do you think there are other mechanisms except for the shear acceleration which could explain these long X-ray jets?
Yeah, I mean, one thing that I was thinking of is clearly, I think, not going to be the answer indeed, because I was thinking also about recollimation shocks, if any, because in principle, what we did for the jet termination shocks might also work there. But I agree, I mean, naively, I would expect that shear flow acceleration is probably more likely. But I think you will hear more about this, probably more dedicated talk in a couple of weeks by Brian.
Yeah, but
we talk more about this part.
My question was actually more general, so it's very interesting. For decades, people are discussing this hard X-rays, Chandra X-rays, Chandra jets, and just stating synchrotron electron, while with some statements, the shocks or something else, but it's clear that shocks cannot explain. Traditional shock cannot explain such a, right? So what I want to say, if this is only shear acceleration mechanism, then why we could not? So what is missing in this mechanism, which is not applied for all this? All these situations is not directly connected to your talk, but you are showing these beautiful pictures. So you address only one thing, the hotspots. That is so that am I right? So that is only
yes. Yeah, but I mean the point is, I mean quite clearly there should be different acceleration mechanisms that work in different places. So that point was, I mean, what I've discussed today was more about the hotspots.
Yeah. Okay.
It's not exclusive at all, and I fully agree that there is particle acceleration elsewhere. I mean, you quite likely also have particle acceleration close to the supermassive black hole in the center. So in that sense, I'm not surprised at all. But then the question is, how do you get suddenly such a large amount of high energy particles just at the end of the jet?
Yeah.
Now, of course, the question as to which one of these mechanisms is responsible for ultra energy cosmic rays, if any, is another question, which is not directly which we can address only after addressing all mechanisms at the same one after another.
Okay, so already more comments, more questions? So it seems not, then I think we should conclude. or the Rashmi Express. I just appreciate your agreeing to give a talk. So we'll have a next talk in 2 weeks. So thank you very much.
Thank you very much again for the invitation, and also for all the very interesting comments.
Okay, bye. Bye.
See you in a couple of weeks. Bye.
Bye, everyone.